Oh, good morning. Did you know that diffusion is a large part of everyone's daily life? One of the first things I do when I wake up. It's diffusion. You know, when you're sleepy in the morning and you need a little pick-me-up, there's nothing like a cup of joe. If you like sugar, this is diffusion. Oh, shoot. Funny thing about that, more diffusion. As you can see here, these are just a few examples. Diffusion is everywhere. It's a great thing.
What is diffusion? Diffusion is the movement of a substance from a region of high concentration to a region of low concentration. What affects diffusion? Two important factors that affect diffusion in a liquid system are temperature and viscosity. Temperature is the energy of motion of particles in a given substance. As you can see, the three gentlemen in the video are fluid particles and are moving slowly. The particle wearing a black t-shirt enters the cold system and also diffuses through slowly. Conversely, fluid particles are moving a lot faster and interacting more in higher temperature systems. The particle is able to move much more rapidly through the higher temperature system. Along with temperature, viscosity is also an important factor affecting diffusion. In a liquid system, viscosity is the fluid's internal resistance to motion. In this quick demonstration, the particle is trying to move through a less viscous system. It is relatively easy for the particle to make its way through the fluid's resistance. As for a higher viscosity system, the fluid has a greater resistance to motion that prevents the particle from diffusing at a fast rate as seen in the video. Here we have the governing equations for our overall experiment. Equation 1 is Fick's law. It describes the flux from an area of high concentration to an area of low concentration. This flux is dependent on the ability of a substance to diffuse in a given medium known as diffusivity. In order to find diffusivity coefficients, we use the Stokes-Einstein law. The equation demonstrates that diffusivity is directly proportional to temperature and inversely proportional to viscosity. We will demonstrate these principles with a two-part experiment. During part 1, we will observe how temperature affects diffusion. For this part of the experiment, we will drop blue dye in 3 vials of water at varying temperatures. Now let's take a look at the diffusion rate for each vial. As soon as the dye is dropped into the vials, it quickly becomes clear. Diffusion of the dye is fastest in the hot water and it is slowest in the cold water. Now for part 2 of the experiment, we will be testing 7 liquids of varying viscosities to see how the rates of diffusion compare. The dyes now drop into the liquids and we can already start to notice differences in the diffusion rates. For instance, hand sanitizer, being the most viscous of the fluids, has the slowest diffusion rate, and water, being the least viscous, has the fastest diffusion rate. Also, as more time goes by, the diffusion rates in all the liquids slow down. We conclude from our experiment that our prediction drawn from the Stokes-Einstein law is supported. We saw from the experiment that as temperature increased, the diffusion rate increased. As for viscosity, diffusion occurs much slower in a more viscous liquid. In our experimental demonstration, we used a very basic visual model of diffusion. There are many other applications of mass transfer in the real world, such as diffusion across membranes in human cells, controlled release of pharmaceuticals, and uses in semiconductors. Chemical engineers play significant roles in all of these diffusion processes by designing innovative ways to develop new products and equipment that are used in all of these fields and more. Thank you for your time in viewing our presentation.